Hey everyone, welcome to The Explainer. So today, we're diving into the hidden mechanics of something that shapes literally everything we see: light. We're going to explore the physics of invisible bending, and honestly, by the time we're done here, you will absolutely never look at a simple glass of water the same way again.
Think about a perfectly ordinary, everyday optical illusion. You take a straight stick, or maybe a straw, drop it into a glass of water, and suddenly it looks completely broken. It gets all jagged and bent right at the surface. Why does it do that? We've all seen it a million times, right? But very few of us actually stop to think about the physical mechanics behind it.
Take a look at this. The physical stick is resting down there at the bottom, at point P. But the image we're actually seeing, it's floating way up there at P prime. And I want to validate what you're seeing right now. This is not a glitch in your eyes. Your brain isn't misfiring. This apparent bending is a strict, undeniable rule of physics playing out right in front of you.
Section 1. The core mechanism. Rules of the speed limit. To solve the mystery of this bent stick, we've got to understand the fundamental rules governing how light travels.
So, the secret behind this whole illusion is a phenomenon called refraction. It's basically the change in the direction of light's path when it passes from one transparent medium to another. Think of it kind of like this. Imagine you're sprinting as fast as you can on smooth, solid pavement, and suddenly you run straight into a pit of thick, heavy mud at an angle. Your speed drops instantly, right? And because one leg hits the mud before the other, your entire direction of travel physically pivots. Light actually has to bend when it hits a new medium for the exact same reason.
Check out the directional rules here. When light travels from a rare medium, like air, into a denser medium, like glass, it slows down, just like hitting that mud. Because of that, it bends inwards, right towards that dashed vertical line we call the normal. But when light does the reverse, going from dense glass back out into rare air, it speeds up, and it bends away from the normal. It's a really predictable geometric dance.
Section 2. The math of light. Understanding refractive index. In physics, we don't just settle for knowing that light slows down. We want to know exactly how much it slows down. Let's look at the actual numbers.
Okay, before we talk about slowing down, we have to establish our baseline. 3 times 10 to the power of 8 meters per second. That is roughly 300 million meters per second. That massive number is the absolute maximum speed of light in a vacuum. It's literally the universe's ultimate speed limit. But here's the catch. Light only travels this fast when there is absolutely nothing in its way. Every other transparent material has what we call a refractive index, which is represented by the Greek letter mu. It's basically a measurement of how hard a material hits the brakes on light. A vacuum sets our baseline at 1.00, 0 slowing down. Water has a refractive index of 1.33. Glass is a bit denser, coming in at 1.5. But look down there at diamond. Diamond has a massive refractive index of 2.41. That means light travels almost 2.5 times slower inside a diamond than it does in outer space. And actually, that incredibly slow speed is a huge part of what gives a diamond its signature sparkle.
Now here's a mind-blowing distinction we need to keep straight. Optical density has absolutely nothing to do with physical mass density. For example, kerosene is physically lighter than water. If you mix them together, the kerosene just floats right on top. But optically, kerosene actually has a higher refractive index than water. So to a ray of light, that floating kerosene is actually thicker and harder to get through than the heavier water beneath it. Crazy, right?
Section 3. Through the looking glass, blocks, prisms, and deviation. Now that we've got the rules of speed and density down, let's see how they play out with specific geometric shapes. Let's see what happens when we introduce a standard rectangular glass block. Follow that incident ray, entering from the top left. It hits the glass, slows down, and bends toward the normal. Then it hits the bottom boundary, escapes back into the air, speeds up, and bends away from the normal. Now, because the top and bottom surfaces of this block are perfectly parallel, the ray that exits is completely parallel to the ray that entered. It just took a little step to the side. We call this lateral displacement. The light keeps its original heading, it's just been physically shifted over a bit.
But contrast that glass block with a triangular glass prism. The rules change here because the sides of a prism are not parallel. In step 1, the light ray enters the prism and bends towards the thicker part, the base. But in step 2, because of that angled surface on the way out, as it speeds up, it bends even further towards the base. So unlike the glass block, this light ray does not continue on its original path. Its ultimate direction has been entirely hijacked.
Notice that angle marked with the little Greek letter delta in the upper right corner? That is the angle of deviation.
By tracing the original intended path of the light forward and the newly altered path backward, we can measure the exact degree to which the prism bent the light away from its target.
Section 4, the grand payoff, solving real-world illusions. All right, we've covered the heavy physics, the math, the indices, the angles. Let's bring all this back down to Earth and finally decode those visual mysteries we started with.
The reason things look so bizarre in water comes down to the difference between real depth and apparent depth. Remember, as light leaves water and enters the air to reach our eyes, it hits a rarer medium, speeds up, and bends away from the normal. This creates a massive discrepancy between where an object physically is, its real depth, and where our eyes actually perceive it to be, its apparent depth.
When you put all this together in a familiar setting like a swimming pool, it totally makes sense. The object, O, is down at the real depth. As its light rays travel up and exit the water at point B, they bend sharply away from the normal to reach your eye. But here's the flaw in human biology. Our brains firmly assume that light always travels in perfectly straight lines. We just don't instinctively calculate for refraction. So our brain traces those bent rays entering our eye straight backward, projecting a virtual image at point I. Your brain is literally painting the object higher up than it actually is. This is exactly why that stick looks broken, and it's why a deep swimming pool can look deceptively, dangerously shallow from the edge.
And this leads to some incredible everyday consequences. It's the reason stars twinkle in the night sky. Their light is constantly being refracted by fluctuating temperatures in our atmosphere. It's why we can actually see the sun a few minutes before it physically rises above the horizon. The atmosphere is literally bending its light around the curve of the Earth. It's why text looks raised under a glass paperweight, and why a coin can seemingly magically appear in a cup just by pouring water over it. This invisible physics shapes our daily reality in so many ways.
So I want to leave you with a little thought to chew on. If our own atmosphere, our water, and our glass are constantly bending and hijacking the light of everything we see, what else in the vast universe are we looking at right now that isn't actually where it appears to be? Refraction proves that seeing isn't always believing. Sometimes, seeing is just a virtual image projected by the rules of physics. Thanks for joining me on this explainer. I really hope it sparks some curiosity, and I'll catch you next time.